done, and let me go to a new page, and let's rewrite the equation. Let's see, let me rewrite this equation. Delta P over delta T. The change in momentum in the x direction over t is just going to be the velocity, and all I'm doing is rewriting it so we can have something on this side to refer to. Then we have our mass being held constant, so delta Vx over t. So we already know what the second portion is going to be. The change in velocity over time is just acceleration, and that's in our x direction, okay? It's the same thing as what we started with. But now we have this new component coming out of this equation, and it is called thrust. So this new component is basically saying, oh, when the velocity is held constant and our mass is changing, such as a rocket engine, or if we move mass, you have propellers, we move mass. If you have jet engines, we are moving mass, okay? Moving large quantities of air. We're heating them up and causing explosions, all kinds of stuff. We can let this side equal to the net force. This was what Newton presented first, okay? So I just wanted to make sure that you knew that if the mass wasn't changing, as in a scenario where we're throwing a ball, like so, the mass isn't changing in this case. So this piece would go to 0. And thus we are back to the net force in the x direction equals to mass times acceleration. Just so we understand what's going on. So what I want to do is say, oh, okay, well, if that is the case, I can write this equation, which is the original equation by Newton, like so. Times t equaling to the change in momentum. All right. The portion on the left-hand side is called the impulse. It's about how long you apply a force to something. If it's a baseball bat and a ball, you're going to apply a force to a ball for a given amount of time. And when you do, you change the momentum accordingly. All right. So impulse, this is our impulse momentum theorem. All right. So we're going to use this idea to come up with the conservation of energy. Basically, if the system is in equilibrium, all right, then we are going to have this scenario, which implies that, I should have gone through all the steps, but the initial momentum in the x direction equals to the final momentum in the x direction. This is the conservation of momentum. I want to say momentum is neither created or destroyed, only transferred. Okay, so you have momentum on one particle, it can be transferred to momentum to another particle. So it's conservation of momentum. So let's see if our video and our worksheet came down. Still looks like it's trying to pull it down. All right, the video is down. So now I can actually look at the video